Okay, good morning, everyone. This is Because You Can Run, You Can't Hide. We're at PyData London. It's Saturday, July 13th, 2019. It's nice to meet all of you. I'm James Powell. You can follow me on Twitter if you like this talk. My Twitter handle is Don't Use This Code. So I'll start off like every talk starts off with who am I, except you probably don't really care that much. So I'll boil it down to the most important parts. Number one, you can follow me on Twitter if you'd like. And number two, I come from a scientific and numeric computing background, not a machine learning background. And so a lot of this talk is about the kind of problems that we solve in the scientific and numeric computing ecosystem. Namely, a lot of us come to Python looking at Python as a glue language, specifically looking at Python as a language that wraps existing C or C++ code. It's often the case that somebody has written analytical code or model code 10 or 15 years ago in C and C++, and we want to provide that to our users in a friendlier fashion. And so when we choose to use Python, we're choosing to use Python to adapt existing code or to adapt an existing API. And our choice of Python, especially for those of us who come to Python prior to, say, some of the nice conveniences added in later versions of Python 3, often isn't that great. We came to Python because there are no core dumps, because there's no malloc and free to add a lot of cognitive overhead, because there's namespacing, but that really only ever means that, okay, yeah, just a little bit less typing. And because Python has some rich introspective features, and so we chose Python because we can work more iteratively. It's not this painful write some code, compile, rerun that code cycle that you often see with C or C++. Now, in terms of when we're using Python, we often see that our use of Python splits us between thinking about Python being used as some library code or some analysis and application code. And a lot of us start our career at that lowest tier, writing analysis code, doing the analyses themselves, using some libraries. And as our career progresses, we move higher up and we start writing library code. Instead of doing the analyses ourselves, we're now in charge of facilitating or empowering our users to do the analyses better. In some cases, we may see even 3 tiers where there's some analysis level, some library level, and some core library level. It may be the case that when we talk about a library, the library that you're writing is something that itself is built on existing libraries like pandas or NumPy. And as you move higher up in the stack, this requirement to be able to do API design becomes more and more pressing because you're no longer responsible for just deriving analysis. You need to facilitate large teams of people to be able to do those analyses as effectively as possible. So you have this necessity to do API design. You need to be able to design APIs so that people can do their work more effectively, where the core of that work is implemented in maybe C or C++, and you're providing some layer in order to shave down the edges, the harder edges of that. Now, again, why Python? If you think about Python, Python or any language in general provides a set of metaphors and a set of mechanisms that make API design easier. And the terminology I'm using here is that a metaphor is maybe something that's provided to the user, a convenience or an affordance that makes it easier for the user to conceptualize how they bridge solving the problem and writing the code that actually solves some business problem. And a mechanism is something that's provided to the author, some tool that makes it easier for the author of this library to provide some code base that they can maintain long term, that their users can continue to use in order to solve real-world business problems. And so when we talk about metaphors in Python, there's quite a few. If you dig back to the beginnings of some of the libraries that we use every day, like matplotlib, they came to be in an environment where Python really didn't provide all that many metaphors on top of, say, C or C++. If you look at the matplotlib API and you wonder, why does it have, first of all, 2 APIs? And why is it such a simplistic API and it doesn't use any of these recent features? Why doesn't it, for example, use properties? It's because matplotlib predates things like properties in Python. And so when matplotlib was first developed, the depth of metaphors provided to it were quite few. I mean, you had metaphors like being able to call a function. You had metaphors like being able to pass keyword arguments. And so you could write some nice code that looks like this. That's way better than what you'd write in C or C++, where this additional optional keyword argument might be obscured by a bunch of null values passed in between or having to create some struct or some object to pass through. Python gave you a much easier way to express the same thing that the core library needed in order to implement some functionality. It provided some basic namespacing, so you didn't have libraries where every function was prefixed by the name of the library, and so your users could type a little bit less. But as Python grew, we started to add deeper metaphors, and so you had object orientation. And when you look at a lot of the libraries, a lot of the older libraries in Python, really they limit themselves in terms of the metaphors they employ to just functions and objects and nothing more. But as you start to look at newer and newer libraries, they use nicer metaphors in Python, like context managers, the ability to prefix and suffix some operation, to bracket some operation with some setup and teardown. APIs like matplotlib predate this, but newer APIs are able to use the richness of metaphors available in Python. There was a talk that I gave that's on YouTube that has like 1 million hits on YouTube, where I go into depth about some of the nice, rich metaphors that are available in Python, generators, coroutines, context managers, and decorators. And you actually have a very rich field in order to provide these conveniences and affordances. Now, when we talk about mechanisms in Python, mechanisms are pieces that are made available to the actual author of this library, stuff like the ability to have variadic arguments or keyword variadic arguments. This makes it a little bit easier for you to, for example, write wrapper functions where you don't have to fix some dependency on what the function you're wrapping, what exact arguments it takes. You can just say it's a star arg, star star quargs, takes any set of arguments whatsoever, and you can free yourself of some of these dependencies that you would otherwise have to deal with. If you really think about it, think really deeply about how difficult it is to use variadic arguments in C, and how, for example, printf has variants like VA printf, and how you can't actually mix and match those. Python, even something as simple as this, is a giant step ahead of what you had available in C, and maybe even C++. Similarly, in more modern Python, you have things like keyword-only arguments. It makes it really easy for you to write a library because you can say, look, my users are no longer fixing on some particular order of the arguments. They can only ever pass these arguments by keyword. In Python 3.8, maybe a little bit more dubious of a change. You have things like positional-only arguments, and so you're forcing users to not fix themselves on the name of an argument. One of the core mechanisms that a lot of API designers try to reach for is an information hiding mechanism. And surprisingly, even though Python has such a rich set of mechanisms available to it, this is one which you can see is stunningly missing. When I say information hiding, I mean things like encapsulation and constness. And so from an API design perspective, you often want to provide your user with like some function from some API. And when you look at that function itself, it has some internal detail, some internal implementation. And you want to hide that from your user because otherwise, if they fix some dependency on this implementation, you lose your ability to move quickly in refactoring the underlying library itself. But it turns out that obviously if you have some implementation function, some user is going to dig around in the module, they're going to find the method that it begins with an underscore isn't going to give them a pause, not a pang of compunction, not a moment of guilt. They'll just import it and use it, and then they'll complain when you change out the implementation later and their code breaks. And unfortunately, or maybe fortunately for the user and unfortunately for the library author, Python is very rich in its introspective capabilities. And so in the standard library itself, you have things like get source from the inspect module. So you can just find what the source code is for any arbitrary function and then figure out how it was implemented and pierce that veil that that library author is trying to put around some implementation details. Or similarly, in the standard library, there's a dis module. And so even if, for example, they only provide you with the Python bytecode and they don't provide you with the source code, you can still disassemble the bytecode and kind of figure out what's going on behind the scenes. In fact, earlier this year, there was a really interesting library that was made available called uncompile6 that decompiles Python bytecode. And it turns out that it is surprisingly easy to make very readable source code given Python bytecode. And so even if you provide the user with only the bytecode, not the source code, they can still do some digging behind the scenes to figure out what's going on. Now, if we think about and we try and focus on just one particular problem, for example, you have some API and you have some state, and you think about how you might go about hiding that state, we'll see that it turns out to be very difficult in Python. So you have some API, you have some hidden state, and you don't want the user to be able to see that state or to muck with it. And so one of the common approaches that somebody would suggest you take is use the property decorator. And so you have some class, you have some property, there's some underscore x state, and the user can't quite see it, they can't quite touch it. Their interface is through this property, and so they can do sets and gets. And if they perform an operation like .x equals here, this will fail. Python will say there's no corresponding setter, and this will fail. But an even slightly competent user is just going to do a dir on this type, and they're going to just change the code to look like this and move on with their life. And they're going to pierce that veil that you've created by using this property. And you might think, OK, now you've changed from being a user to being an adversary. Let me see if I can step it up a bit, and I can make it a little bit harder for you to pierce that veil. And so you might be motivated to try something a little bit crazier. Instead of hiding this state in behind a property, but where the state is still visible, you might hide the state by creating some lambda, and this X is now hidden in the closure of the lambda, and so if they do that dir, they can't quite find it, but a sufficiently motivated user is just going to say, you know what, I can swap out that lambda and get along with what I was trying to do. And it turns out that if they wanted to do this even more surgically, they can, with just a combination of dir and just looking at what's available at that object in their interactive console, they can dig deeply enough and find, you know what, I can actually go into the function closure where that state was, the cell contents, and I can see what those cell contents are. Now, if they try and change those cell contents, as we know, Python closures are read-only, but that user can say, you know what, Python has a very rich runtime. In a Python runtime, everything exists, everything is visible, and there's got to be a way for me to do what I want to do. I want to go in and I want to muck around with this internal state. And so what they're going to determine is, even if you try and make this much harder for them, and you try and say, I'm going to hide this in a method that I'll delete out of the scope, that I'll hide in the default arguments here, what they're going to do is they're going to say, you know what, I can dig around and I can find that const. I can try and change it. That won't work. But what I can do is, it's Python. It's got a rich runtime. I won't try and change it. I'll just make a copy. I'll make a perfect copy of the thing that you have and just swap out the one piece that I wanted to swap out. And so here's a little bit of code here where we just copy somebody else's function and swap out the read-only parts with the parts we wanted to modify. And then if you do that, you can go very deep into that function and you can find where the data is stored and make a copy there. You can make a copy of the next level up, which happens to be where that function is bound in the default arguments. Then you can make a copy one more level up, which is on the fget of the property itself. And if you put it all together, you have something that looks like this, and you've ended up patching out this 3-layer attempt to block the user from seeing some internal state and mucking around with it. And this is the safe and easy way to do this. Now, when I say that this is not hard, this is an easy way, I really genuinely mean it. That's not hubris, that's not showing off. Yes, if you look at some code that looks like this might be bewildering. And it may be the case that if you look at this, you can't quite write that out from scratch off the top of your head. If you looked at code like this that makes a copy of that function and swaps out the consts and the defaults, you might not be able to write that off the top of your head, but really genuinely consider this. When you have a user who is sufficiently motivated to break the veil of some API because there's something that they need to get done for some process and the library you have provided them is not able to do what they need to get done, they have infinite time, they have debuggers, they have dir, they have introspective abilities, they have a runtime, they have access to all of your source code, they have Stack Overflow, and while they may not be able to write this off the top of their head, any sufficiently motivated user over the course of a couple of afternoons or a couple of days, if they really want to break that veil of that API, they will come up with this. If they can't come up with this themselves, they will Google until they find some Stack Overflow post where somebody else came up with this, and they'll use that. And so it turns out that in Python, these mechanisms are sufficiently, they're not very protective. There's no way for you to hide information using any of these mechanisms because even it really isn't the sophistication of the user in terms of their knowledge of Python. It really is the motivation of that user that's going to determine whether they're going to be able to pierce this veil or not. Now, you could even do this more surgically. It turns out that when you're mucking around with Python internals and you're doing your dir and seeing what you can read and write, yes, it turns out the Python interpreter itself has certain portions that are read-write. For example, the function closure has some read-only portions that are not writable. And you can play around with some tricks to copy things around. And you might say that in the real-world case, the level of complexity of the code that you're trying to surgically make modifications to is so high that it's not actually feasible for you to go and find a surgical way to change that. And this is the same reasoning behind why if I, for example, deliver model code to a user and that model code is in the form of a binary blob, I'm not really worried that they're going to reassemble the assembly back into C code and make modifications. It's probably not a very realistic thing. When a company like Adobe gives you a binary blob for Photoshop, they're not really worried that you're going to go and patch bits in there because the level of complexity is too high. But it turns out that Python's runtime is so dynamic and so capable of introspection that these techniques tend to be much easier than you'd expect. And there's always some layer where somebody can dig just deep enough and look around and inch their way towards figuring out how to defeat one of these mechanisms. In fact, something that we discovered when we were diving into this from a different perspective is that there's even more surgical and maybe less safe ways to go about doing this. It turns out that tuples aren't really immutable in Python. Now, what I don't mean is I don't mean that you can do something like that. That's not true. I mean, obviously, this is going to fail. This tuple is immutable. And I don't quite mean something like this, where, yeah, the tuple contains a list, and the list is immutable, and you can do that, and you don't get any trouble. And I don't mean something like this, where if you actually try this in your Python console, the Python console will tell you it failed, but it'll actually succeed, which is the worst of both worlds. And I don't mean that. What I mean is, if you dig into, say, the disassembly for a function like this, and you look at the disassembly for that function, and you see that at the very top of that disassembly, there's this method called load fast. And you dig into the C code for CPython, and you look at what the load fast does. You can see there's a get local on line 1075. And you look at what that get local macro does, and you can see it does an array index into this array called fast locals. And you think for a second, you say, hold on, it's doing an array index, but it's not checking the extents of that array index. So if you gave it a bad local variable to load, you could arbitrarily read and write into memory to your heart's content. Well, that's how you can actually make tuples mutable. And so this is something that we discovered last year. And this is the practical use case for it. It turns out that if you automatically generate a Python function, and that Python function has 2 to the 16th branches in it, and you dynamically create that function until that function was within 2 to the 16th bytes of some code you want to manipulate, then you can tell that function to change a local variable that doesn't exist, that happens to be at exactly the offset where the memory you want to mutate is, and you can go and you can change that memory. And the surprising thing about this approach is there is no C code here, there is no C types, there is no CFFI, there is nothing that is not in the standard library that's not just creating Python code by execing a string of text and abusing bytecode values. So it turns out that it's surprisingly easy to poison bytecodes without anything even looking like C, and break any Python sandbox, twiddling bits to your heart's desire. So this is an example of tuple set item. I thought it was a really cute little example that we came up with last year that shows, look, the situation of Python is such that there are so few mitigations, the language is so dynamic that any attempt to do information hiding can be defeated. Now, if any of you have had an opportunity to see some of the talks going on at EuroPython, there was a talk this weekend about PEP 551 and I think 557. I was part of the authorship of that PEP and some of the previous work of it. It was about auditing hooks being added to Python. Python 3.8 now has auditing hooks, and this is part of a larger effort to add security transparency features to Python. This is not adding features to Python from the perspective of API design. It's adding features to Python from the perspective of making it able to run in very secure execution contexts. And it turns out that there is some similarity between the things that you need to do when you're trying to do information hiding and the things you might want to do when you're trying to lock down a Python interpreter. And exploits like the one that I just showed you there show that it is incredibly difficult to lock things down. Oftentimes, I found when I have looked at code bases and I have wanted to pierce the veil of some encapsulation that API gave me so I can make the API do something it wasn't supposed to do because I need that in order to do some work. I've often found that the resource that I go to is traditional hacker text files to figure out how would a hacker go about breaking this, and that's how an API user would go about breaking this as well. Now, it turns out that for the most part, a lot of the code that we're writing is running on Linux, and the situation is even worse than you thought. Because it turns out that on Linux, you might have a proc file system. In this proc file system, all those numbers there are all the processes that are running on my computer right now. There's a symlink there, self, and that's the current process. In that current process, you can see there's 2 interesting files here, one called maps and one called mem. And this maps file tells me all of the maps, all of the locations in virtual memory where I have allocated something. So you can see this is in the less process, so you can see the first 3 are the actual less binary. You can see there's libc here as well. If this were a Python process, I would see all the dynamic libraries that Python itself loaded. And the really sad thing is, if you look at the permissions of mem, which represents your virtual memory, it's read-write. If you go into the kernel itself and you look at how the proc file system works, you can see there's that mem object. And Here's where the mem operations are. Here's where the write operation is. You have to go a little bit deeper. When you actually write to the proc self mem object, it only looks at the file permissions of the file, not of the memory segment. So even though some of these memory segments are marked as read only, execute only, none of that is obeyed if you write through the proc file system. So it turns out that this, R not or R XOR X protection, W XOR X protection, this memory is either writable or executable. Even that can be defeated trivially. Or in other words, some of these mitigations that I'm showing you that work in Python are generalizable to any language whatsoever. If you give me a programming language like C++ or Java, and I have the ability to open and write to a file, I can flip bits in that language. There is no information hiding in Python. There is no information hiding in C++ or Java that will defend against a sufficiently motivated attacker. Because that attacker can always dig into system memory itself and flip bits to their heart's content, find whatever they want. The only boundary you have provided by the operating system is the process level boundary. And in Python, it's quite easy to come up with an interesting use case of this. So here is image write. Oh, that's my Twitter page. Here is, follow me on Twitter. Here's image write. And just an example of you take a string, a byte string in Python, and you can make byte strings in Python mutable by just going into the virtual memory of the process itself and flipping bits in the virtual memory of the process itself. And so there is no information hiding mechanism that you can guarantee will defend against a sufficiently motivated adversary, where I use the word adversary as a synonym for end user. So what does this all mean? What's the point? Other than showing you a couple of cute little hacks, what's the point of all of this? Well, it turns out that we may be thinking about the way that we design our APIs wrong if this is the perspective that we're taking. APIs are not wholly programmatic. If you think about it, the meaningful construction as part of a software process is a human construction. It is a human being who cares about the API, and if you think about software as a discipline, it's very difficult for us to call software engineering. There is no such thing as software engineering. We don't really obey any of the general principles of any other engineering field, despite calling it software engineering. But if we wanted to find an argument by which we could defend software as an engineering practice, it would be that software is not a mathematical or scientific process. It's a process that is subordinated to some human effort. The software only makes sense in terms of what it helps a human being do, and that's akin to what we might call engineering. In other words, if you think about writing code, there's some automation spectrum between what a machine can do automatically and a human can do. All of these mitigations and all of these attacks and counterattacks that I've talked about, we're considering only the machine side. But there's a human side as well. For example, if I provided you with an API and it had a load data function, and it had a clean data function, and maybe I used a metaphor so you have keyword arguments that you can provide as well, and there was a process data function, and I was doing a code review of the code that you gave me, and in the middle I saw this. It doesn't matter that you can do this. This is going to get blocked to code review, right? Because you're not going to say, oh, that looks reasonable, and then they put that in the middle, and oh, OK, yeah, OK, of course. And so what it means is all of these API mechanisms that I'm trying to use to do information hiding, yeah, you genuinely cannot do it. You cannot enforce it at the machine level. But it's very trivially easy to enforce this at the code review at the human level. And so I think one of the core lessons that we should have here is we shouldn't care about our users. And I know some of you are saying, you know what? Why did I have to see this talk in the first place? I already don't care about my users. So maybe I'll adjust this slightly. Adjust the way that you are concerned about how your users use your code. Ultimately, the users of some API are highly paid professionals. The reason that they are trying to work around something that your API has done, they're digging into the implementation details, they're making it harder for you to maintain that code, they're perhaps piercing the veil, they're breaking your information hiding mechanisms, is because they have assessed that this is what's necessary to do in order to accomplish some human task, and I'm not going to prioritize something that the machine tells me that I can or can't do over what the human or the business needs me to do. And I'd say even in the PyData audience, an increasing topic recently has been things like linters and code formatters and things like PEP484 type hinting. And all of these mechanisms, when they're presented to you at a conference, like a PyData conference, they're often presented to you as an assistive mechanism. Oh, you should use an auto formatter like Black. It really helps you out. Oh, you should use PEP484. It really helps you. in writing your code and refactoring your code more effectively. But unfortunately, when you see these same mechanisms employed in an industrial setting, you're no longer told, oh, you're going to start using PEP44 because it helps you out. Oh, you're going to use auto-formatting because it helps you out. They turn into coercive mechanisms. Oh, you're going to use PEP44 because your code sucks and we need to force you to write code the right way. Oh, your code formatting is all over the place. You need to use an auto-formatter like Black because otherwise your code is unreadable. And it turns out that this statement of my coworkers can't code is a universal statement. It doesn't matter where you work. It doesn't matter how much you're paid. Everybody seems to complain about the poor code that their coworkers write. But this is owing to a misconception. It's a misconception of, one, are your coworkers are they given the proper incentives to write good code? And if not, maybe the code they've written is because they're working under some incentive structure that incentivizes them to ship things over shipping good things. Or maybe they're working around legitimate problems in an API or a platform that you have provided them that they have assessed, this is the only way I can get done what I need to get done. In other words, the easiest place to find a spotless kitchen is at a restaurant that has no customers. Or the easiest place to find perfect code is if nobody uses that code. To put it more formally, you can think that in any business function, if the core process of that business function involves software, and that business function is in a competitive market, that software is going to continuously be pushed to do more and more, to expand into other areas, to scale in whatever it means for that to scale, and so that software will always operate in a degraded mode. There is no core process of a successful business in a competitive market where that software is not operating in some kind of degraded mode. And so that code will always be bad, it will always have problems, it'll always need somebody to come in and fix it. This is why I'm actually very skeptical when we talk about safety in an industrial setting and whether that's applicable to software, because I don't know that it's actually genuinely structurally possible for commercial software safety to even exist, given the incentives to push that software always outside of its proper operating mode. So the lessons that we might learn from this is, when we started off in this discussion, I said the easiest way that you might implement software hiding in Python is using properties. And when we found that we could break that, we started going into deeper and deeper mechanisms and seeing that none of those actually worked. Well, it turns out that some of these basic techniques are sufficient. That very first technique, you want to hide something, use a property, and then use code review in order to ensure that people don't abuse that. The basic techniques end up working, and as you go into these deeper and more convoluted techniques, you end up not gaining anything but you can have an arms race between you and your users to see who can work around whom most effectively. Similarly, maintain constant communication with your users. If your view is that your users are adversary and they need to be coerced into using your library in the correct way, and you're not constantly in communication with them to say, how are you using this? What do you need out of this? And what is it not solving for you? You're going to find that you're going to be pushed to these mechanisms to say, I'm going to force you to stop doing this by hiding some information here, by blocking something here, by doing something crazy that they will then find a way to work around. Similarly, write as little code as possible. Because as you saw those mitigations become more complex, the amount of code that the author of those mitigations had to write became greater. Their requirements to focus on things to coerce their user into doing the right thing started to outpace the actual functionality they were providing, and this wasn't a good story for anybody. And ultimately, keep that code shallow. Keep these mitigations, keep the code shallow enough so that if you have some convenience layer and that convenience layer has certain conveniences associated with it that the user might want to work around, it's okay that they might pierce that veil. They will do that. They will dig into the implementation. They will take a nice convenience API that you provided them and dismantle it to get something done. Assume that that's going to happen. Keep your convenience layers as shallow as possible so that you can recode or reformulate those convenience layers when you see that they are piercing that veil. And assume that this misuse is going to happen. Don't try too hard to avoid the misuse. In fact, anticipate that you'll get things wrong and write your code so that if the API that you wrote was wrong and a user had to dismantle that API to look at something that you were trying to hide, some state or some implementation detail you were trying to hide, anticipate that that will happen. And in fact, try to give them safer safety valves. Give them a way to safely break your API. Give them a way to escape out of certain mechanisms that you're enforcing upon them, because they will do that no matter what, and so try and work with that. And ultimately, remember that because you can run Python, because it is such a rich runtime, you can't hide. Thank you so much.
If anyone has questions, you want to open the Q&A? I think there are 10 minutes.
We can answer any questions that anybody has.
Yeah, thanks.
Who thinks their coworkers don't write good code? You can close your eyes so that if you're sitting next to your coworker, yeah. Who thinks their coworkers write really great code and oh my goodness, I'm so happy? Don't lie, don't lie.
It's amazing talk, thank you. What tool do you use to make those gorgeous slides?
I'll answer that at the pub quiz. Any other questions? Oh, follow me on Twitter. Yeah. Oh, I don't know. I think it's somewhere on the screen somewhere. I can.
Sorry, yeah. So you're talking about the safety hatches and escape hatches and stuff like that. Presumably it's just flexible and thin, shallow layers, like you're saying. But can you give some sort of examples of where you've seen that work well and kind of like what that looks like? Yeah.
So I think if you look at Python itself as a core language, and if you look at it in comparison to other languages, look at the sys module in core Python, and look at all the ways that you can patch or revise certain assumptions that are made. You know, if you want to print something to a file, the print function has a file keyword argument, or you can just rewrite standard out and it just works. If you look at a lot of core libraries, you don't see these kind of safety hatches or safety valves, or escape hatches or safety valves really added to them. And think about cases where, I'll give you an example of where it fails. Have you ever tried to subclass a NumPy ND array or subclass a pandas data frame? It doesn't work, does it? Because you have this problem of always falling out of the type. And in certain cases, you may actually need to do that. You may need to subclass the ND array in order to intercept certain operations. And when you do that, you end up finding yourself in this weird, degenerate case where you have to overwrite, or you have to implement every single operation on the pandas data frame or the NumPy ND array in order to make sure that you don't fall out of that type. And then as those libraries are updated out of sync with the library that you have to maintain that. Here's a case of there being no safety valve, no escape hatch, because somebody somewhere wanted to do something. They had this data frame object that was wrapping around some underlying storage. You didn't really provide them a way to get down into that underlying storage without digging around. And you have this arms race or this unfortunate situation where you're working around something that they did, and then they may end up trying to either work around something that you've done, or they may end up writing some code that breaks your workaround.
We have still 5 minutes, so if there is more questions.
Hey, thanks a lot for the talk. I just wanted to, can you just explain what you meant a bit more about keeping your code shallow? I didn't completely get that part.
One of the things that you see is, if you look at an API like Pandas, or you look at an API like Matplotlib, or if you look at an API like Bokeh. Bokeh used to have the Bokeh charts and the core Bokeh, and the general idea was there was some level of that API that implemented the core functionality, like the actual construction of the visualization, and there was some layer on top that filled in a bunch of details that would make it so you didn't have to specify the mark type or the color or whatnot. So you had this two-tiered API. Matplotlib very much has this, the PyPlot API. Does anyone here actually use raw Matplotlib? No, you always go through PyPlot and then you pass in arguments. Well, look at the stack depth for something like PyPlot and see if you do pyplot.hist, how many layers deep you have to go to figure out where that code is actually generating the items that fit into the Matplotlib draw graph. And it tends to be very, very deep. If any of you have dealt with things like Python packaging, see how deep it is between where your setup tool's entry point is and where it actually calls into the code itself. You're looking at maybe 5 or 6 stack frames deep. And while that may not sound like such a big problem, consider that if you wanted to look at something like matplotlib.pyplot.hist, and you wanted to slightly modify something about how it generated its graph, if you have 4 or 5 stack frames deep, where that argument that you're passing in at the hist level is getting used is the possibility for where that's going to use is going to exponentially grow with each stack frame. Each function that gets called now has a new set of places you have to look. And so with a very deep API like that, you end up having to look in a lot of places and potentially having to patch out a lot of things to make the necessary changes. And so a better API would be if you had as few stack frames as possible between that convenience layer and the actual core layer. If you had a convenience layer like PyPlot, and I'm not saying that this is so trivial to do, because clearly in the case of matplotlib, it is a library that was written by very talented people, and so they've tried their hardest to do this. But in that convenience layer, if it was as shallow as possible, if it had as little code in terms of the number of stack frames, then it would be a lot easier for somebody to read the code for that and then re-implement their own version or to patch out the pieces they want to actually get down into the core functionality layer.
We have a few minutes for last question.
Could you talk a bit about why people want to hide the state from the users?
Yes. I've written some convenience layer for you. That convenience layer makes a lot of assumptions. It maybe hard codes some configuration. I'm very opinionated about the configuration. It uses some underlying mechanisms, like think about pandas plotting. And when you do pandas data frame.plot, there are certain assumptions that are made in terms of what backend do you use, what options do you use, how do you construct that plot, right? Now, if you have the ability to pierce that plot API and you're digging deep into the internals of how pandas plotting works, and you're then writing your code against that, and then pandas updates to support new backends, the pandas authors are going to write code that breaks your code. You're going to go onto GitHub, and you're going to fill out a GitHub issue saying, Mark Garcia, I hate you so much. Why did you break my code? And it's going to ruin his life. And so the reason that they want to hide those implementation details and make it harder for you to find them is because that's how they preserve their own sanity. For when they need to make underlying changes, they want to provide you as small an API as possible so that they can track what you're dependent on, so that they don't end up accidentally making one small change that seemed very reasonable to them, but then broke a lot of people's code, and they get a lot of angry comments on GitHub.
Time is up, unfortunately. If you want to ask more questions, please do offline. And thanks to James Powell for his talk.
Thank you so much.